Have you ever just stopped and looked at the world around you? I mean, really looked at the skyscrapers that seem to touch the clouds or the massive bridges that connect our cities? They all stand on a foundation, but it's one you can't see. And today, we're going to pull back the curtain and show you exactly what it is.
And that's really the heart of it, isn't it? Before a single piece of steel is cut, before any concrete gets poured, the entire project, every last bit of it, is built with something else entirely. It's built with the pure, universal language of mathematics. That right there, that's the real blueprint.
So let's kick things off with the big why. In this first part, we're going to explore why math isn't just some hurdle you have to clear in school. No, it's the fundamental tool. You might even say it's the very soul of the entire engineering craft. You know, you can think of it like this. An engineer uses math to have a conversation with the physical world. It's how they ask really important questions like, hey, is this beam actually going to hold the weight? Or is this design truly safe for people? And math gives them a definitive, non-negotiable answer. It's the language they have to speak to turn a cool idea into a solid reality that won't fall down.
So what does this language actually do? Well, it breaks down into these core functions. Math is what ensures safety by letting us calculate all the loads and stresses. It's what controls costs by making sure we get the quantities exactly right. It helps us optimize materials. It enables razor-sharp precision in our designs. And maybe most importantly, it helps us reduce risk. These aren't just boxes to tick off a list. They are the absolute pillars of any responsible engineering project.
Okay, so if math is a language, then what are the specific words in the grammar? Let's crack open the engineer's toolbox and take a look at the essential math disciplines that they absolutely have to master. First up, the absolute bedrock, basic arithmetic and algebra. This is the day-to-day workhorse. It's used for something called quantity takeoff, which is just a fancy way of saying the super detailed process of estimating every single material you need for a job. We're talking every screw, every wire, every bag of cement. Getting these simple equations right is what prevents huge budget overruns and crazy delays down the line. Next in the toolbox is geometry, which is the math of space and shape. This is how engineers take a flat blueprint, a drawing on a piece of paper, and understand how it's going to exist in the real three-dimensional world. From calculating the exact volume of concrete for a foundation to laying out the precise coordinates of a building on a piece of land, geometry is what makes the abstract physical. And that leads us perfectly to the next level of precision, trigonometry. This is the mathematics of angles and relationships. It is absolutely crucial for surveyors mapping out land, for calculating the perfect pitch of a roof, or for figuring out the exact angles for structural supports. Sine, cosine, and tangent aren't just things you memorize for a test. They're the tools that make sure everything fits together perfectly. And now for the heavy hitter, calculus. Look, if geometry can describe a bridge just sitting there, calculus is what describes how that bridge behaves when a fleet of heavy trucks drives over it during a windstorm. It's the math of change and dynamic forces. It tells us how beams bend, how water flows, how structures respond to stress. Honestly, it's the true backbone of any advanced structural analysis. But of course, the real world is messy. It's not perfectly predictable, and that's where statistics and probability come in. This is the math of uncertainty. It's used for quality control checks on materials, for analyzing the risk of something failing, and for forecasting project timelines. It's what allows engineers to make smart, informed decisions based on data, not just on guesswork. Finally, we've got the engine that powers all our modern engineering software, matrices and vectors. When engineers use these incredibly powerful programs for complex analysis or for building information modeling, BIM, it's matrices that are crunching millions of complex calculations in the background. You don't see them, but this is the math that powers our most advanced digital design tools today. Okay, so we've got our toolbox full of all these powerful concepts. But now, let's see them in action. How do these kind of abstract ideas connect to the day-to-day work of real-world engineers? This table just lays it out so clearly. You can see how it all connects. A structural engineer, they're living in the world of calculus and matrices to analyze complex forces. A quantity surveyor, their bread and butter is arithmetic and algebra. An urban planner needs statistics and geometry to design cities that actually work for people. It's all about picking the right tool from that math toolbox for the right job, every single time. In all of this, every tool, every calculation, it all boils down to one simple, unavoidable, and incredibly powerful truth. A single mistake in the math, one misplaced decimal point, can have catastrophic consequences in the real world. So let's be clear. Without math, there is no such thing as safe construction, period.
This brings us right into the modern era. How do all these timeless, ancient mathematical principles translate into the cutting-edge software and algorithms that are literally building the world of tomorrow? So yeah, on the surface, an engineer's toolkit today looks a little different. We've got BIM, Building Information Modeling, which creates these super smart 3D models of entire projects. We've got powerful software that analyzes structures, and even AI that can optimize designs for peak efficiency. We can simulate entire smart cities on a computer now. But here's the thing you absolutely have to remember. Technology hasn't replaced math. Not at all. It has amplified it. Every single one of these sophisticated, high-tech programs is, at its core, just a really, really complex expression of those fundamental math principles we've been talking about. So let's bring all this home. What does this actually mean for you? Whether you're a student thinking about jumping into this field or a young professional who's just starting out, let's look at the final equation. This is probably the single best piece of advice anyone can give you. Don't just try to get through your math courses. Don't fear them. You have to embrace them. You have to master them. Because trust me, mastering math is the key that will unlock your entire potential in this industry. You know, in engineering, the equation is incredibly simple and it's totally unforgiving. Weak math skills directly translate to weak, unsafe structures. There's just no way around that truth. But here's the equation for your career, and it's a lot more inspiring. Strong math skills don't just build strong structures, they build a strong, successful, and really impactful future for you. So I'll leave you with this thought. The foundation of our entire built world rests on mathematics. That's a fact. The only real question left is the one you have to answer for yourself. How strong are you going to build your foundation?